Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss about the expression for coefficient of friction in terms of shear stress. So in our last lecture, already we have derived an expression for the loss of head when it is flowing through a pipe. So this relation also similar to that last lecture expression. So here also to identify this coefficient of friction in terms of shear stress, we need to also consider the pipe flow. So first of all, let's draw a pipe, okay, through which the fluid is flowing, and you can just draw like this. And this is not. Yeah, and now let's draw its center line of this pipe. Yeah, and the fluid is flowing through this. Okay. So this fluid is flowing with a velocity of capital U, or as I told, capital V. Okay. Now, when it is flowing through this pipe, so we know that there is some losses will be there, and as well as the losses, there is some, loss of energy or loss of head, what we can say. Along with that, we can say that velocity of this fluid near to this wall or near to this pipe is considered as a 0, and this is happening due to the viscosity of the fluid. Okay, this one already we have discussed in the last lecture. Now here what I'll consider, so to identify this expression, actually I need to see what are the forces are acting, in this fluid flow. Now forces are acting in the fluid flow, if I consider, then only one force will come. Now while to derive this expression, I need to consider two different sections in the pipe. So let me consider one section here, another section here. So this one you can give a name of section 1, and this is you can give a name of section 2. Okay, section 1, section 2. Now we need to consider the fluid flow in between this section 1 and section 2. Okay, though the fluid is flowing through this total whole pipe, so to identify or to apply a Bernoulli's equation in this concept, we need to consider at a fixed 2 points. Okay, so now we can apply the Bernoulli's equation here. Okay, section 1 and section 2. And what are the forces are acting at this point? Now suppose at this point the intensity of pressure which is acting here, which is in the forward direction, in the direction of flow, and another one intensity of pressure which will be acting at the reverse direction of the flow, and this is P2, because section 2 is there, we can consider this one. Okay, and the friction factor or the frictional force which will be also opposite to this one, and this one we know that F1. Okay, we can give a name of only F or F1, we can give anything, no issue in that. So what I meant to say here, so for this kind of conditions, what are the forces are acting in this fluid when it is considered as the section 1 and section 2. So I can write here what is the force. So we can write the we know that pressure equal to force by area, and when the force will be calculated, we can write pressure into area, and this force is nothing but the pressure force which is acting on this. So now I can write the pressure force at the point of at the section 1, I can write P1 into A, and similarly the pressure force at section 2, we can write this is similarly P2 into area, pressure intensity of pressure into area. Okay, now next is third one, is another one pressure is there, another force which is known as the frictional force, so that one also acting in this, so that is F1 we can consider, there is frictional force. Okay, now these things already we already discussed in the previous lecture also, but for this also, this is for this derivation, this expression also required, that's why I'm reminding you. Now we'll go for the resolving of forces. So resolving of forces is nothing but we can consider the summation of x equal to 0. Okay, so summation of which direction? In the direction of fluid. It may be in the x direction, because the fluid is flowing in this x direction, you can see, because it is a horizontal pipe. So you can consider summation of f equal to 0. Okay, Now, what are the forces are there here? Total forces. Here one force is there, that is P1 A, and this is reverse direction, this one opposite direction, which is opposing this fluid flow. So we can consider this is minus P2A, and next is F1, which is F1, a frictional force. So this is also reverse direction, okay, equal to 0. Now what I'll do here, I'll just take common A here, P1 minus P2 bracket A, and this force I will take to other side, F1. Okay, this is the frictional force. Now this frictional force also we can write, this is the force due to the, see how this force is generated, and this force also can be written like, you know, the shear stress or the force due to the shear stress. Okay, the force due to the shear stress. So what I can write here, F1 I can write the force due to shear stress, due to the shear stress, that is nothing but tau naught we can consider. And this also we can write, this is force due to shear stress. So you can write here, this is shear stress into the shear area, or you can write the surface area which is covered here. So this is also same thing. This also we know, we can write, we know that stress equal to force by area. Okay, now here also we can write force equal to stress into area, and this is the stress, shear stress, which is considered. And why the shear stress we have considered here, as I told you already, because there is a pressure, like, you know, velocity gradient is there, and due to that the velocity at this point surface is 0, and as the height increase, okay, as it goes beyond from this wall, the velocity of the value of velocity also increasing, and due to this here the pressure, that velocity gradient is in, like, you know, created, that is del u by del y. And this concept we have discussed in the Newton's law of viscosity, that is nothing but tau equal to shear stress equal to mu into du by dy. Okay, so now this one we can write here, shear stress into surface area. So shear stress we can write tau naught due to the shear stress, and surface area is nothing but, here I can write pi dl. What is the surface it's covering? Okay, this L is nothing but the distance between this section 1 and section 2, and d we can consider the diameter of the pipe here. Okay, now so this is about what, a P1 minus P2 here, and this A part I can consider here, or you can write here itself, no issue. Let's write here, then we'll go for that. Now here in the place of A I can write pi d square by 4. We know that area. Okay, so area of the pipe we can write pi by 4 d square. So now here pi d we can cancel, so only one will be there, d. So that one we can write P1 minus P2. So only d is there, so that d we can, and this 4 take it to right hand side. So 4 tau naught into L divided by this, only one d will be there, equal d square, one d cancel, so one d is there, this is d. So this one we can give expression 1. So previously any expression need to give, yeah, this one we can give an expression 1, or this one we can give expression 1, and this one we give expression 2, equation 2. Okay, now here we got the pressure difference here value. Now previously also we have seen from the Bernoulli equation there is a pressure difference was there. Okay, so from the Bernoulli equation, if you remember, this is P1 by rho g plus V1 square by 2g plus Z1 equal to P2 by rho g plus V2 square by 2g plus Z2 plus HF. So these things we have already seen in the last lecture video as per the Bernoulli equation. This is correct. So now if I'll say Z1 and Z2, this is the Z1 and Z2 is the nothing but the height of this pipe from a datum line. So let's consider a datum line. From that, whether the height of this section 1 and height of the section 2 both are same or not. Here you can see this is the horizontal condition. So we can see this is Z1 is equal to Z2. Okay. Now again, when the diameter of this pipe is same at the section 1 and section 2, so this velocity also will be equal. So these two will be cancelled. Velocity equal to how? Now we know that, again I can write here as per the continuity equation, Q equal to AB, I can write A1 V1 equal to A2 V2. Now see, area is same, diameter is constant for all this section 1 and section 2, so area also same. So area same means velocity will be same, so velocity for this term also will be same. Now from what we got here, HF you keep one side, HF equal to, we can write P1 by rho g minus P2 by rho g, and this one we can write what, P1 minus P2 by rho g. This is the value of HF. Okay, now what I'll do, I'll just take the same value here and I'll put this in this equation. Now I can write HF equal to, here HF equal to, I can write P1 minus P2 by rho g equal to another one equation we got in the for deriving the previous video lecture, Darcy-Weber's equation for the frictional loss or major loss, we can say. So that one also we know that is 4FL B square by 2dg. This is the equation, Darcy-Weber's equation. This equation you can give equation 3. Now just we need to solve this equation, that's it. So what I'll do, yeah, this is, and here we can write HF equal to, now see, this is equation. Now here what I'll do, I'll just take this rho g this side and I'll keep P1 P2 minus P2. This is one expression. So from this equation, equation 3, I can get what? From this equation 3, I can write what I can write. Now I want to know this value of P1 minus P2, what? Now that is 4FL B square by 2dg into rho g. So here gg will be cancelled and we can write this is 4LB square into rho by 2d. This is equation 4 you can give otherwise. Okay, now what I'll do, I'll just compare this equation 2 and equation 4, because at this both the left hand side P1 minus P2 is there. So just correlate this equation, we can get it. What? Let's see this equation, 4 tau L by D, 4 tau naught L by D equal to, here what we'll get, now 4 LB square rho by 2D. GG cancel already. Okay, now if you compare this equation, DD here cancel, and here 4 also can be cancelled. Now what we need to identify, as I told you, we need to find out the value of in terms of shear stress, the coefficient of friction in terms of shear stress we need to identify. So here what we'll get, just we keep the shear stress one side, that is tau naught. Okay, and here also L will be cancelled here. Now what is the final value will be there? Now tau naught equal to F V square by 2, F V square by 2, and rho is there also. So rho F B square by 2. So this is the expression for the shear stress in the coefficient of friction. Now if you want to just change this equation also, we can write in this way also. This is, we can write F equal to 2 tau naught divided by rho V square. This is also can be written. So this is the expression for the shear stress in terms of for the coefficient of friction, and this also we can give in equation 1, equation 6 for this. Okay, so I hope you understand this equation. So how to derive this shear stress in the terms of coefficient of friction. Okay, that means the expression for the coefficient of friction in terms of shear stress. So this is the shear stress expression and this is the coefficient of friction expression. So if you want to keep the shear stress one side, like in terms of to identify the value of shear stress, we can use this for, you can use this value. Same things like the friction, coefficient of friction F. Okay, so in this coefficient of friction F, you can see tau is there, that means shear stress is there. That's why the expression for the coefficient of friction in terms of shear stress. So you can see the expression of coefficient of friction in terms of shear stress is there. So I hope you understand this expression. If you are having any doubt and query regarding this, you can give a comment on the comment box. Thank you all.